Relation and function is the first chapter of class 12. To learn that chapter, we need to know what are the things you learned in 11th standard about relation. For that, first you studied what is an ordered pair. So you know the two objects taken in a particular order, that is what is called an ordered pair. Example, A comma B. This is reading as ordered pair A comma B, where A is the first element and B is the second element. Then two ordered pairs are equal only when the first element are equal, second element are equal. A equal to C, B equal to D. This symbol means if this is there, we will get this, and similarly if this is there, we will get this. Means AB equal to CD, then A equal to C and B equal to D. Reverse order. If A equal to C and B equal to D, then ordered pair AB equal to ordered pair CD. Then you studied in 11th cross product. Suppose A and B are any two sets, then A cross B equal to, you know how to make it. The cross product elements are ordered pairs in which the first elements are taken from A and second from B. So 1, 3, 1, 4, 2, 3, 2, 4. That is A cross B. And you study number of elements in A cross B equal to number of elements of A into number of elements in B. So this is set 1. So 1, 2, 3, 4 elements are there. One element is ordered pair 1, 3. This is one of the elements, second, third, 4 elements are there. That is 2 into 2. Number of elements in A is 2 and number of elements in B is also 2. So there are 4 elements, and you studied A cross B contains. This A cross B contains 2 raised to 4 this elements. That is 2 raised to 4, 2 raised to number of elements in A cross B is equal to 16 subsets. And each of that subset is called a relation. Each of that subset, that 16 subsets you can write, which you learned in the last year. Each of that is a relation from A to B. Or we are writing R dot A arrow mark B means R is a relation from A to B. Or also we can write R is a subset of A cross B. Phi is called the void or empty set, that also is empty relation, and A cross B is the universal relation. That much you studied in 11th standard. Then some additional things you studied is, if R is a subset of A cross A, or R is a relation from A to itself, A to A, or we are saying R is a relation on A, all these three sentences are in same meaning, then A cross A, we know, this is A cross A. A is already here, 1, 2. Then second element is also from A and A itself. So 1, 1, 2, 2, 1, 2, 2, that you studied. 1, 1, 1, 2 like that. A itself you have to repeat again. That is A cross A. 1, 1, 1, 2, 2, 1, 2, 2 is the universal relation. And from here you studied identity relation on the set A. It is denoted by IA, I suffix A. Means identity relation on set A. What is that is? You write only the equal elements of A. A and B must be equal. First and second element must be equal. No other elements are present in identity relation. Equal elements are only present. That is what is called identity relation. Or in the short we are saying that identity IA is, that is identity relation, is set of ordered where AB such that A is equal to B, where A and B are belongs to this A. That much also you studied in 11th, or some students are not learned this in 11th. So that is an identity relation. Then 12th standard we are starting types of relation, that is one is reflexive relation. Reflexive relation on a non-empty set. We are writing non-empty sets only, non-empty set A. This is what is non-empty set. means minimum one element must be there, that is non-empty set A. So reflexive relation on a non-empty set A is, if you want to say it is reflexive, A comma A belongs to R. For all A belongs to A, this symbol is for denoting for all A belongs to A, means any element is present in A, for all of them equal elements must be present. Identity relation also like that, but the problem coming is identity relation, additional elements are not possible, only equal elements are possible. But in reflexive relation, first element and second element equal, that is compulsory. Additional element may present. One of the example is written here. A is equal to set 1, 2, 3, 4. A is equal to 1, 2, 3, 4. This is non-empty set. One of the relation I wrote here. 1, 1, 2, 2, 3, 3, 4, 4. This is identity relation also, as well as reflexive relation also. Means if I want to say this is reflexive relation, each of these elements must have a equal element present. 1, 1, 2, 2, 3, 3, 4, 4. None of them must miss. Every element must present. Additional element also possible. That is why another relation is written. 1, 1, 2, 2, 3, 3, 4, 4, 1, 2. That also reflexive relation. The third one is written. 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3, 4, 1, 4, 4. You need to see only 1, 1, 2, 2, 3, 3, 4, 4 are present or not. 1, 1, 2, 2, 3, 3, 4, 4. Other elements, we are not bothering about other elements, all the equal elements must present. One more is written, R4 is equal to fourth relation from here itself. 1, 1, 2, 2, 3, 3. But it is, the last one is not reflexive because 1, 1 is there, 2, 2 is there, 3, 3 is there, but who is not there? 4, 4 is not there. So not reflexive because 4, 4 not belongs to R. So R means R4. R4. Let us see the second type of relations now. So let us see the second relation, that is symmetric relation. Symmetric relation on a non-empty set A. It is a conditional relation. Condition means depends upon the element you are writing in R. Suppose you are writing A comma in B in R, A comma B in R, means A is related to B. Then you must write B comma A belongs to R. Whatever the order is writing, its reverse order also must present, then only it is symmetric. Means if AB you are writing in R, A related to B, then B also must be related to A. Example, A is equal to 1, 2, 3, 4. If we are writing only 5, R1, 5, symmetric. No element present. 1 comma 1, reversing 1 in itself, so it is also symmetric. 1, 2 wrote, then 2, 1 also must be written. Reason? 1, 2 is written, 1 is related to 2, so 2 also must be related to 1. You see the fourth one, R4 is equal to 1, 1, 2, 3, 3, 2, 2, 4. Is not symmetric because 1, 1 is written, 2, 3, 3, 2, all reverse order, but 2, 4, 4, 2 is not present. So it is not a symmetric. So what is transitive relation? It is also conditional relation. Here how? If A is related to B and B is related to C. See, A related to B. This B is related to another element. Then the first and last element also related. AB and BC if you are writing in R, then AC must be written. If you are writing only AB, not a problem. But AB followed by BC you are writing anywhere, then the first and last also must present. A comma C also must present. Example. A is equal to 1, 2, 3, 4. If we are writing R1, 5, not a problem. It is transitive. Symmetric also, transitive also. If we are writing only 1, 2, not a problem because 1 ending with the 2, no element is starting from 2, not a problem. But here you see R3, 1 comma 2, 2 comma 3, 1 related to 2 as well as 2 related to 3. So 1 must related to 3. See the next one, R4 1, 2, 2, 3, 1, 3, 2, 1. Is not transitive because 1, 2 is there, 2, 1 is there, first and last element. 1, 2 is there, 2, 1 is there, 1, 1 also must present, 1, 1 is not there. Similarly, 2, 2 is also there, not there, or any one of that. Any one is only required to show. See that 2 is related to 1. Now come back. 1 comma 2. It is a set. You can write elements anywhere. 2 comma 1 followed by 1 comma 2, so that this 2 related to 1, this 1 related to 2, so 2 must related to 2. That is also not there, so we can say it is not transitive. This is another example showing some conditions are satisfying a is equal to 1, 2, 3, 4. If I am writing 1, 1, 2, 2, 3, 3, 4, 4, means these 4 elements. It is already reflexive. 1 comma 2 is also writing, then it will not be symmetric because 2 comma 1 is not present. Not symmetric. And it is reflexive as well as transitive. Reflexive as well as transitive is there, but not a symmetric, because 1 comma 2 is there, 2 comma 1 is not present. In R1, 2 comma 1 is not present in R. Let's say another example, R2, 1, 1, 2, 2, 3, 3, 4, 4, so reflexive. 1, 3, 3, 2, 1, 3 is written, 3, 1 is not written anywhere, so not symmetric. This is also not transitive because 1, 3 is there, 3, 2 is there, 1, 2 is not there. Yeah, you may see that 1, 4, 1, 4 is also not there. You can see what's the reason. 1, comma 3, 3, comma 4. 1, 4 is also not there. Any one of the example. You can see another one. 4, 3 is there. Come back 3, 2, 4, comma 3, 4 related to 3, 3 related to 2. So 4, 2 is not also not present. So any one of the example you show. So it is not transitive also, but it is reflexive. What about this? 1, 2, 2, 1, 1, 1. Not reflexive because 1, 1 is there, but 2, 2, 3, 3. None of that is present, so not a reflexive, but it is symmetric as well as transitive. We can write a lot of examples like that. Now, what is an equivalence relation? Any relation which is satisfying reflexive, symmetric and transitive. If all the three are satisfied, then such relations are called equivalence relation. So, A is equal to 1, 2, 3, 4. If we are writing identity relation and a universal relation, identity relation IA and A cross is universal relation. Both of them are equivalence relation. So, where any non-empty sets, two equivalence relation always will be there. One is identity relation and other is universal relation. So, always will be there. Now, one question is written: R is equal to set of ordered by where A, B such that A minus B is divisible by 5, where A and B are natural numbers. You take the natural number in such a way that their difference is divisible by 5. For example, 1, 6. 1 minus 6 is divisible by 5. 1, 11. 1 minus 11 is divisible by 5. Such a numbers. Lot of examples are there. How we can prove it is an equivalence relation? Let's see. So A minus A means what I am writing is if I can write A comma A, then only reflexive. So if I am writing first element also A, second element also A. For example, 1 comma 1, 1 minus 1, 0. 0 is divisible by 5. 2 minus 2 divisible by 5. So 0 is divisible by 5, 0 is divisible by every number except 0. So A minus A is equal to 0 is divisible by 5. Therefore I can say A comma A belongs to R, then only reflexive definition is there. For any natural number n, for all, means any natural number you take, it will always satisfy. So R is reflexive. Let's see symmetric. A minus B is divisible by 4. For example, 1 comma 6. 1 minus 6 is divisible by 1 minus 6 is divisible by 5. Therefore, 6 minus 1 also divisible by 5. That is written A minus B is divisible by 5. Implies B minus A also divisible by 5. 1 comma 11 also divisible by 5. 11 comma 1 also divisible by 5. Any order you write, not a problem. Negative numbers are also divisible by 5. Therefore, we can say AB belongs to R implies BA, means if we are writing A related to B, then BA also there, B related to A. So you can say R is symmetric. Let's see transitive. A minus B, B minus C. Two consecutive elements. 1 comma 6 and 6 comma 11. Both are divisible by 5. So their sum, for example 10 and 15. 10 is divisible by 5, 15 is divisible by 5. Their sum 10 plus 15, 25 is also divisible by 5. That is why I added A minus you will get A minus divisible by 5 means A related to B and B related to C implies A related to C is there. A, B and BC are in R. then AC also must be in R. That is transitive relation. Therefore, R is a transitive as well as equivalence relation. So let us see what is equivalence classes. Equivalence classes. Equivalence class, the word you can define only when equivalence relation is there. If you are proving an equivalence relation, then only we can say equivalence class is present. If not equivalence, it is not an equivalence relation. If any relation is not equivalence, then equivalence class, the word you cannot use. Means always reflexive, symmetric and transitive, then only. Now, equivalence class of an element A is denoted by the square bracket A, just like a greatest near function. But when you are reading in a relation, it is reading as a equivalence class of A. What is this equivalence class of A is, in a relation, what are the elements related to A in the ordered pair? If A is there, then A will be related to another element. So that set is called the equivalence class of A. Example. Just now we proved R is equal to set of ordered pair AB such that A minus B is divisible by pi, AB belongs to N is an equivalence relation. Then equivalence class of 1 means what are the elements related to 1? Means the numbers when you are taking the difference with 1, which are the numbers which are divisible by 5. 1 1, 1 minus 1 0 is divisible by 5. 1 6, 1 minus 6 minus 5 divisible by 5. Similarly 1 11, 1 16. So we can say equivalence class of 1 are 1 6 11 16 etc. Same equivalence class is for the 6 also, 11 also, 16 also. If we are writing an equivalence class, then all the elements present in that set having same equivalence classes. Similarly 2, 2 minus 2 0, 2 minus 7 divisible by 5, 2 minus 12 divisible by 5. So equivalence class of 2 is this, same as 7 and 12. Similarly 3, 3, 8 etc. same as 8, 13 etc. Like that's a way to write equivalence classes. So two equivalence classes never have two different equivalence classes never have a common element. You see 1, 6 etc. None of these elements will be present here and none of these elements will be present here. Different equivalence classes. Then another example is written now. Suppose L1, L2 etc. are lines in a plane. Means we are considering the lines in a plane such that lines are parallel, L1 and L2 are parallel. You will write on this R only when L1 and L2 are parallel. Then it is an equivalence relation because every line is parallel to itself. So L1 comma L1 is belongs to R because L1 is parallel to L1. Every line is parallel to itself. So R is reflexive. So L1 L2 belongs to R implies L1 parallel to L2. If you want to write L1 L2 belongs to R, then L1 must be parallel to L2. If the first line is parallel to second line, then the second line always will be parallel to first line, which implies L2 parallel to L1 means L2 L1. I started with L1 L2, but I reached L2 L1 belongs to R. Therefore, R is symmetric. Similarly, for transitive, I took L1 L2 L2 L3. You see, here ended, started, same number started. L1 parallel to L2, L2 parallel to L3. Means all these lines are parallel. L1 parallel to L2 and L2 parallel to L3 implies L1 parallel to L3. Means L1 and L3 belongs to R. I took these two, so I got L1 L3 also. Therefore, R is transitive as well as equivalence because all the three satisfy. But if you are writing L1 perpendicular to L2 in the same cases, in the same case, then it is only symmetric because L1 perpendicular to L2 implies L2 perpendicular to L2. If one line is perpendicular to the other one, then the second line is perpendicular to the first one also. But a line cannot be perpendicular to itself, so L1 cannot be perpendicular to L1, so not reflection. L1 perpendicular to L2 and L2 perpendicular to L3. First line perpendicular to second one, second line perpendicular to third one, but first cannot be perpendicular to third. So R is not a transitive. So it is not a equivalence relation also, because it is satisfying only symmetric relation.